Every year, the world churns out over 90 million cars, but only a handful of factories on the planet can assemble a body that looks like it was squeezed from a single mold. In Texas sits a machine weighing 410 tons that presses with a force of 9,000 tons, more than 25 Boeings combined. 8 of these giants work non-stop, birthing a new part every 90 seconds. How does one press stroke replace 70 parts and hundreds of weld points? Stick around till the end. You'll see how metal is rewriting the rules of the auto industry. When Tesla decided to install these presses at their Texas factory, a question came up. How do you even deliver a monster like this? Because the Giga Press is manufactured in Italy by Hydra Group. The distance? Over 5,900 miles across an ocean and a continent. You can't ship the press in one piece. It gets broken down into 500 separate components, each requiring special handling. The heaviest parts, the press frame and hydraulic cylinders, weigh 30 to 40 tons each, which means no regular truck can handle them. For transport, they deploy a special convoy of 50 heavy-duty semi-trucks. Picture a line of trucks stretching over 3,000 feet, rolling down Texas highways at no more than 30 miles per hour. Each truck carries a piece of the giant, from massive steel beams to precision hydraulic systems. The toughest part? The main press frame. It's so massive it needs a special platform 80 feet long with 80 wheels. This thing is so wide it takes up 2 lanes of traffic. Police shut down roads, escort the convoy, warn other drivers. Locals come out to watch this industrial caravan roll by. You don't see that every day. At the plant, the real challenge begins: assembly. A team of 50 engineers and technicians works around the clock for 3 months. Special cranes with 400-ton lifting capacity hoist the press sections, connecting them inch by inch into a single structure. Picture the complexity. You need to align parts to within half an inch. If the frame is off by even a degree, the press won't work. Laser levels continuously monitor the geometry. Engineers adjust positions with hydraulic jacks, tighten thousands of bolts with precisely calculated torque. When the press is finally assembled, it takes up nearly 100 feet by almost 50, the size of a small supermarket. Inside this metal beast hide 6 hydraulic cylinders, each 20 inches in diameter. They generate pressure capable of crushing a car into a tin can in 1 second. But the most incredible part? The first startup. When 410 tons of metal come alive, the factory floor shakes. Hydraulics hiss, metal groans, and a massive 20-ton plate slowly descends with 9,000 tons of force. It's so powerful that the foundation beneath the press is reinforced with 10 feet of armored concrete. Otherwise, the machine would punch straight through the floor. And that's just one press. Tesla installed 8 of these giants in Texas alone. Each one costs around $20 million. Together, this armada of metal titans transforms the plant into the most advanced car manufacturing facility on the planet. Now for the most interesting part, how this monster machine actually works. Picture what happens inside the Giga Press every 90 seconds when a new Cybertruck part is born. It all starts with aluminum. Not ordinary aluminum, but a special alloy developed specifically for die casting. Aluminum ingots are loaded into a massive melting furnace positioned right next to the press. The temperature in the 2 medium-sized furnaces reaches 1290 degrees Fahrenheit. That's hotter than molten lava. At this temperature, solid metal transforms into a silvery, almost mirror-like liquid. The aluminum melts completely, flowing like water while maintaining its metallic density. 1 cubic foot of this molten magma weighs 168 pounds. The furnace constantly stirs the molten metal to keep the temperature uniform throughout. Even a 15-degree difference can ruin a part. When the aluminum is ready, a robotic system opens the furnace gate, and the molten metal pours into a special chamber, the hot pot of the press. This happens in seconds because the metal can't be allowed to cool. The exact amount, 88 pounds of weak aluminum, is automatically dispensed with ounce-level precision. Now for the most dramatic moment. Hydraulic cylinders activate instantly. A 20-inch diameter piston injects the molten aluminum into the mold with insane force. Injection speed hits 30 feet per second, faster than a professional baseball pitcher's fastball. The pressure is insane, 9,000 tons, or 18 million pounds of force. To picture that, it's like 25 fully loaded Boeing 747s pressing down simultaneously on an area the size of a dining table. Under that pressure, liquid aluminum fills every microscopic corner of the mold in 0.03 of a second, faster than you can blink. The mold is made from special tool steel capable of withstanding extreme temperatures and pressure. Inside, channels of complex geometry are cut, mirroring the contours of the Cybertruck's rear or front body section. The mold's machining precision is 0.005 of an inch. Any looser, and the parts come out defective. But there's a problem. When molten metal hits the cooler mold, it tries to solidify instantly. If that happens too fast, you get pores and cracks. So the mold is preheated to 400 degrees Fahrenheit, hot enough to slow the cooling, but cold enough for the metal to set in a reasonable time. Inside the mold, a real battle of physical processes unfolds. Liquid aluminum under immense pressure fills the space, forcing air out through microscopic vent channels. Simultaneously, the metal crystallizes, atoms lining up into a solid structure at a rate of 1,000,000 crystals per second. The entire factory floor fills with that distinctive metallic screech and hiss. The press holds pressure for 2 minutes. During this time, the aluminum completely solidifies, transforming from liquid to solid part. The temperature plummets from 1290 degrees Fahrenheit down to 300. The metal contracts, taking its final shape under the watchful eye of sensors monitoring every millimeter of the process. And then the robotic arm extracts the freshly cast part. It's still hot, 250 degrees Fahrenheit, glowing with a dull reddish tint. This massive aluminum panel stretches 20 feet long, weighs just 120 pounds, yet replaces 70 separate parts that used to require hours of welding. Perfect geometry, no seams, no weak points. And all of this in 90 seconds. By the time you heard that sentence, the Giga Press already spit out the next part. 24 hours a day, 365 days a year. And so we can be together every week, subscribe to my channel. What you just saw rewrites every rule of car manufacturing. Traditionally, the rear section of a car consisted of 70 separate stamped parts. Picture this, 70 pieces of metal that had to be cut, bent, fitted together. Then an army of 300 welding robots joined these parts into a single structure. 400 weld points, miles of seams, hours of work. Every seam is a weak spot where a crack or corrosion could show up. Now it's all one monolithic part. No seams, no joints, no weak spots. A solid chunk of aluminum, cast in 90 seconds. Strength jumped 30%. No weak points where the structure can come apart. In a crash, impact energy spreads evenly across all components instead of concentrating on welds. Before, manufacturing the rear section required 300 operations, dozens of dies for each part, massive factory floor space for welding. Now, one press, one mold, one operator. Production costs dropped 40%. Manufacturing time shrunk from hours to minutes. Every year, the world produces over 1,800,000,000 tons of steel. That's enough to build thousands of bridges, but only one of them will become North America's longest cable-stayed bridge, the Gordie Howe International Bridge. 125,000 tons of metal, over 1,000,000 bolts, and a span of nearly 3,000 feet with not a single support in the water. How do two countries stitch steel together over a river? And what happens if even 1 millimeter goes wrong? Stick around to the end, and you'll see the moment when American and Canadian metal literally kiss in the sky. The birth of the steel backbone for the Gordie Howe Bridge starts long before the first beam reaches the construction site. This is a cross-border industrial operation where the Canam Group plays the starring role. The steel for this project isn't just metal. It's the result of collaboration between American and Canadian steel giants. Sheets of high-strength specialty steel are forged at mills in both countries. Then massive rail cars funnel them towards specialized fabrication shops. When you walk into a Canam plant, the first thing that hits you is how modern robotics tames raw matter. You won't see blacksmiths with hammers here. Laser systems and giant computer-controlled machines rule this space. Steel plates several inches thick are cut by laser or plasma with precision down to tenths of an inch. That's critical because each edge girder is made up of dozens of elements that must fit together perfectly during welding. The most dramatic moment at the plant? Assembling that famous box girder beam. Massive magnetic cranes hoist steel plates 49 feet long and position them into specialized assembly jigs. Here begins a process engineers call submerged arc welding. It's an automated technique where the welding head travels along the seam, hidden beneath a layer of special powder, flux. This prevents metal spatter and ensures perfect joint quality. Inside, the beam is reinforced with countless stiffener ribs. These are vertical steel partitions that prevent the structure from deforming under the colossal weight of the roadway. Every weld passes through the hands of inspectors armed with ultrasonic and X-ray flaw detectors. On the Gordie Howe Bridge, there's no room for average quality. If they find even a microscopic air bubble inside the metal, the part gets rejected. After welding, the finished beam heads to the shot blasting chamber, where its surface gets cleaned to a shine, then receives multiple layers of special polymer coating. This is armor against moisture and salt, designed to protect the steel for 100 years. Folks, check this out. I'm standing at a safe distance right now, but even from here, this thing looks completely unreal. We're used to the word beam, but on the Gordie Howe International Bridge project, that term takes on a whole new meaning. Each of these edge girders is a 100-ton steel titan that's literally twice my height. I've watched them get moved. It's a full-on special operation. Giant multi-axle platforms creep slowly across the construction site, and the gravel literally buckles beneath them. When they lift one of these beams into the air, it blocks out the sky. That's the moment you realize there's nothing impossible in this world for someone who's learned to tame steel at this scale. This is pure, raw, 100-ton power that's about to become part of the longest cable-stayed bridge in North America. Ever build with Legos as a kid? Now imagine one piece weighs 100 tons, and instead of plastic connectors, you've got a blazing welding arc. We're on the banks of the Detroit River, and what you see behind me, engineers call an assembly node, but I'm calling it a playground for giants. The assembly process for the Gordie Howe International Bridge means building giant modules right here, on the ground. You can't just hoist one beam and clip it together in the sky. First, on special steel jigs along the shore, these 100-ton edge girders get welded into single sections. It looks incredible. Two parallel edge beams connected by cross-steel trusses, forming a massive frame. When a section's complete, it resembles part of an aircraft carrier deck that someone decided to build in the middle of an industrial zone. Why do they do this on shore? Because here, welders have something they don't have at 492 feet up: stability. Every seam, every joint has to be perfect. I walked up to these guys. They're working in special masks with fresh air supply, because the welding intensity here is so high that the air around them literally burns up. You see these welds? They're as wide as my palm. Robotic welders pass dozens of times over the exact same spot, laying down layer after layer to create a monolithic joint that no storm will ever tear apart. Now look at these bolted connections. Where welding can't be used, thousands of high-strength bolts take over. Each one is tightened with such force that the steel plates start working as a single unit through friction force. When a section like this is fully assembled, they check it with laser scanners. Accuracy has to be within an inch. If there's even a hair's width of misalignment, literally the thickness of a matchstick, then midway across the river, when the Canadian side meets the American side, they just won't line up. The feeling of being next to one of these sections? Pure adrenaline. You're standing inside a steel box that's about to hang over a gorge, carrying thousands of people. The sound here is something else. Constant grinding of metal, hissing of pneumatic tools, and the rumble of heavy cranes. Across the water, slow and almost silent, a massive barge glides forward. Resting on its deck is the very section we saw on shore. A steel frame with edge girders weighing hundreds of tons. From the bank, it looks like a surreal steel island drifting between two countries. But the moment that barge locks into position directly beneath the bridge span, the air gets electric. You look up, and 150 feet above the water, you see the red jaws. Special lifting devices mounted on the edges of the completed spans. What engineers call the heavy lift is beginning. This isn't a quick process. When the winches start working, the steel cables tighten like strings on a giant guitar. You hear that sound? That low, guttural groan of metal accepting colossal weight. The section slowly lifts off the barge. The first few feet of empty space appear between the water and the steel bus. In that moment, all the weight of this monster bears down on the pylons and cables. You literally see the bridge settle a few inches, coming alive under the load. I stood on the shore, holding my breath. Surveyors with laser rangefinders track every millimeter of lift, second by second. And then, when the section finally lines up with the bridge edge, the most critical part begins. The iron workers, who look like tiny dots against the white beams, start catching the section. They use hydraulic jacks to perfectly align the bolt holes. This is the moment when American and Canadian steel has to kiss. When the first pin slides through both plates, a wave of relief you can physically feel washes over the construction site. Its main span is 2,799 feet. That's a massive pile of steel hanging over water with zero support in the river. That makes it the longest cable-stayed bridge in all of North America. Over 125,000 tons of structural steel went into this thing. Constant corrosion from salt water. There's enough metal here to build 1.5 Kitty Hawk-class aircraft carriers. And what about the fasteners? Connecting all these massive beams took over 1 million high-strength bolts. Each bolt is a tiny guarantee that this backbone will handle 100 years of use and more than 2.5 million trucks every single year. It's a genuine metal ocean, tamed by human ingenuity. Did you enjoy this journey from cutting up aircraft carriers in Texas to the birth of new titans in Detroit? If so, you know what to do. Hit that steel bell, smash the like button, and make sure to subscribe to the channel. Right now, you're holding the result of an African tragedy in your hands. Inside your smartphone, laptop, gaming console are tiny components made from a metal mined in the jungles of Congo, where actual wars are fought over it. This is coltan, a dull black rock that looks like an ordinary river stone but costs thousands of dollars per pound, and without which no modern electronics would work. Millions of people have been killed for this rock. Its extraction finances armed groups, destroys guerrilla reserves, and turns people into slaves. But without it, your phone wouldn't exist. Let's peer into the dark world of the most controversial mineral of the digital age, where every like and every post carries the price of a human life. First, the terminology. Coltan isn't an official mineral name. It's short for columbite tantalite. It's an ore containing two metals, niobium, which used to be called columbium, and tantalum. It's tantalum that makes coltan so valuable. It's a silvery gray metal with a unique combination of properties. It doesn't corrode at all, withstands extreme temperatures, has high capacitance, and barely conducts electricity because of a thin oxide film on its surface. That last property revolutionized electronics. Tantalum is used to make capacitors, components that store and discharge electrical charge. Tantalum capacitors are microscopic, the size of a grain of sand, but they have enormous capacitance. They're stable, reliable, work for years without degrading. Every smartphone contains 40 to 50 tantalum capacitors. A laptop, up to 100. Gaming consoles, cameras, even electric toothbrushes. Tantalum's everywhere. Coltan looks like black or dark gray rock with a metallic shine. Heavy, density around 8 grams per cubic centimeter, almost like lead. If you pick up coltan, you feel it's unusually heavy for its size. It occurs as coarse crystals or grainy masses in granite formations. Nothing special to look at, just a rock. But you can get anywhere from $100 to $400 per kilogram, depending on tantalum concentration. The main problem with coltan is geography. About 60% of the world's reserves are in one place. The eastern provinces of the Democratic Republic of Congo, especially Kivu and Ituri. This is one of the most dangerous regions on the planet. For decades, there's been a civil war involving dozens of armed groups that control the mines and use the profits to buy weapons. The story of the coltan rush began at the turn of the millennium. In the early 2000s, demand for tantalum exploded due to a boom in mobile phone and gaming console production. Sony released the PlayStation 2, Nokia and other manufacturers were churning out millions of phones. The price of coltan skyrocketed from $30 to nearly $400 per kilogram. A real gold rush started in Congo, only black. Tens of thousands of people dropped everything and headed into the jungle to dig for coltan. Armed groups seized control of the deposits. Murders, rapes, forced labor began. Kahuzi-Biega National Park, home to mountain gorillas, was overrun by miners. Animals were killed for meat, or simply because they got in the way. The gorilla population plummeted by 90% in just a few years. The UN published a report confirming that coltan sales were financing a conflict that had claimed millions of lives, the bloodiest war since World War II. Armed groups controlled the mines, forcing local populations to work for free or for pennies, smuggling coltan through Rwanda and Uganda, selling it to middlemen who shipped it to China and Europe for processing. Coltan extraction in Congo is mostly artisanal, meaning small scale, no machinery. Miners work in rivers and streams, washing ore in pans like gold prospectors. Coltan's heavier than regular sand and pebbles, so it settles at the bottom of the pan. Or they dig pits in the forest, sometimes 30 feet deep, with no reinforcement. Cave-ins kill people regularly, but nobody keeps track. The working conditions are horrific. People stand waist-deep in murky water all day long, washing tons of rock for just a few pounds of coltan. They make $1 to $5 a day, more than farming, but still poverty. No safety, no rights. Kids work right alongside adults. Women are forced into labor, or worse. Coltan gets collected, dried, and sold to local traders. They haul it to regional centers where Chinese and other foreign companies have warehouses. There, they weigh the coltan, test the tantalum concentration with handheld analyzers, pay cash. Then they ship it out by plane or truck through neighboring countries, Rwanda, Uganda, Burundi, to mask where it came from. Rwanda officially exports hundreds of tons of coltan every year, even though it has almost no deposits on its territory. It's obvious what's happening. It's a transit point for Congolese coltan. The international community knows, but stopping the flow is hard. Borders in the region are porous, corruption thrives, tracing the origin of a specific shipment is nearly impossible. The coltan gets shipped to China, where most of the processing facilities are concentrated. There, it's melted in electric arc furnaces at temperatures exceeding 3,600 degrees Fahrenheit. What comes out is slag containing tantalum and niobium oxides. This slag gets treated with hydrofluoric acid, producing fluorides, which are then reduced to metals through complex chemical processes. Tantalum is incredibly refractory. Its melting point is around 3,000 degrees Celsius, third highest after tungsten and rhenium among all elements. That makes processing energy intensive and complex. Extracted tantalum is converted into powder, which is then pressed, sintered, and turned into anode foils for capacitors just a few micrometers thick. A tantalum capacitor works simply. Thin foil is coated with an even thinner film of tantalum oxide, which acts as the dielectric. Thanks to the microscopic thickness of this film and the massive surface area of the porous structure, you get enormous capacitance in a microscopic volume. This allows electronics to be compact. Without a tantalum capacitors, smartphones would be the size of bricks. Legal coltan mining exists. Australia, Brazil, Canada have deposits and extract coltan using industrial methods that comply with environmental and labor standards. But the cost is higher because you have to pay decent wages, maintain safety standards, and rehabilitate the land. Congolese coltan, extracted through what's essentially slave labor, is cheaper, so demand for it persists. There are also synthetic alternatives. Ceramic capacitors based on barium titanate can replace tantalum capacitors in some applications. They're cheaper and aren't linked to conflict. But for the most compact devices with high reliability requirements, tantalum remains irreplaceable. Military electronics, medical implants, aerospace equipment, they only use tantalum. Tantalum demand holds steady, around 2,000 tons a year. That doesn't sound like much compared to the millions of tons of copper or steel, but given its rarity and concentration in one region, even that amount creates enormous pressure. Every new smartphone, every data center, every 5G cell tower requires tantalum capacitors. Tantalum prices fluctuate between $150 and $300 per kilogram for the metal, or the equivalent for ore depending on concentration. For comparison, gold runs about $60,000 per kilogram. Tantalum's cheaper, but you need way more of it. And extraction is concentrated in a conflict zone, making it strategically critical. The environmental fallout is horrific too. The Congo jungle, one of the planet's largest tropical rainforests after the Amazon, is home to unique species. But artisanal mining is wrecking ecosystems. Forests get chopped down for mines and miner camps. Rivers become polluted with washed-out rock that kills fish and aquatic life. Poaching thrives. Miners hunt wild animals for food. There are attempts to recycle tantalum from electronic waste. Old cell phones, computers, devices contain tantalum capacitors. Technologies exist to extract and recycle them, but economically it's tough. You have to collect massive quantities of old devices, disassemble them, isolate tiny components, remelt everything. Right now, only 5 to 10% of tantalum comes from recycling. Some activists are calling for a boycott of electronics, or at least mindful consumption. Don't swap your smartphone every year. Repair instead of tossing it. Buy used. But here's the reality. Most people don't even know about coltan and the problems tied to it. Manufacturers don't advertise the dark side of their shiny gadgets. There's hope in technological progress. New types of capacitors are being developed that could eventually replace tantalum ones. Graphene supercapacitors promise even higher capacity in smaller sizes. But mass production is years, maybe decades, away. For now, tantalum remains a critical element of the digital age. The irony? Congo is one of the poorest countries in the world, despite its incredible wealth of natural resources. Cobalt, coltan, copper, gold, diamonds, all buried in Congo's soil. But corruption, conflict, and exploitation by foreign companies mean that wealth never reaches the people. It's a classic resource curse, when natural resources become not a blessing, but the cause of endless wars and suffering. Every year, thousands of tons of valuable timber around the world get turned into shavings, and only a few pounds become works of art. Picture this. An 11-pound block disappears in 10 minutes, giving birth to an object lighter than your smartphone. But what actually happens in that moment on the lathe? Why does a single mistake, 1 millimeter off, destroy months of work? And why are some species of wood more expensive than gold, unfazed by water, fire, or time? Today, we're diving inside a process where speeds hit thousands of RPM, and wood behaves like metal. Stick around till the end, and you'll discover the secret behind why these materials sing in music, last for centuries, and why craftsmen work with them almost like living beings. The lathe is simple genius. The blank mounts between centers or in steadies, spinning from 50 to 2,000 revolutions per minute, while high carbon steel or carbide cutters strip away the excess. The craftsman holds the tool in hand, controlling pressure and angle. 1 millimeter off, and everything goes sideways. The process starts with rough turning. The lathe eats wood layer by layer, revealing texture, color, shine. Shavings fly like confetti, filling the workshop with the scent of fresh bark. First, the roughing gouge cuts the diameter down to shape. Then the bowl gouge forms the vessel, and the finishing tool polishes to a mirror finish. The speed is stunning. From an 11-pound blank, in 10 minutes, you get a piece weighing 2.5 ounces. Finish with oil or wax. The wood glows. Not every tree works for the lathe. You need species with uniform grain, no knots, no cracks. Rosewood, or palisander, the king of exotic lumber, hailing from the tropical forests of India, Brazil, and Madagascar. Its heartwood stuns with a violet-red hue that darkens over the years into a rich wine color with black and gold streaks, like a marbled masterpiece of nature. The surface feels oily to the touch. The wood is saturated with resins, which make it gleam like a polished ruby and give off a subtle sweet rose fragrance that lingers in the workshop for hours. Its physical properties make rosewood a turner's dream. Density of 53 pounds per cubic foot, Brinell hardness of 5.5, 3 times harder than oak, yet flexible as bamboo. On the lathe, it cuts like butter. Shavings fly off in thin ribbons, won't clog the blade, won't crack from centrifugal force. The fibers are elastic, so bowls with walls just 1/10 of an inch thick don't split, and candlestick stems survive drops from 3 feet up. The natural oils protect against fungi, beetles, and moisture. Pieces last centuries without varnish. From rosewood, craftsmen make whiskey tumblers for you. The shape is graceful, walls thin enough to see the drink through. The wood's aroma enhances those oak notes. From Indian rosewood, they make sushi sets. Boards, spoons, holders. The contrast of red with white rice looks refined. Often combined with other woods. Rosewood plus olive equals a vase with double shimmer. Gibson Les Paul guitars have rosewood fingerboards. The sound is warm, sustained, with deep bass. Stradivarius violins featured rosewood fittings. Today, it's used for saxophone and flute mouthpieces. The material resonates across all frequencies. Rosewood veneers go onto yachts, Steinway pianos, palace tables. The hardness allows polishing to a mirror finish. An unvarnished surface looks like lacquered obsidian. Working it demands skill. Dry and shade for months, because sun exposure causes cracking. Cut with sharp carbide blades. Dull ones bog down in the resins. Final touch. Linseed oil or carnauba wax, which brings out the purple undertones. Heat treatment makes the wood fire resistant and nearly black. Red sandalwood, a sacred exotic species from the tropical forests of southern India and Sri Lanka, valued higher than gold thanks to its unique red coloration and magical properties. The heartwood has a rich garnet red color that, when soaked with water or oil, takes on a blood red hue, like a genuine ruby embedded in wood. The surface is smooth, with a subtle sweet aroma reminiscent of vanilla and rosewood. This scent lingers for years, filling spaces with the warmth of the East. Its physical properties make it a turner's dream. Density of 69 pounds per cubic foot, heavier than oak or rosewood, high hardness, but flexible fibers that allow creating thin-walled pieces without cracking. On the lathe, it cuts slowly, demanding sharp carbide tools. The shavings come out fine and red, like brick dust. The oiliness is natural, so finishing oil just enhances the inherent luster, making the surface look like polished garnet. Best for premium tableware and ceremonial pieces. Turners craft bowls for Ayurvedic ceremonies from red sandalwood. The red color symbolizes Kundalini energy, and the wood absorbs meditation vibrations. Chalices for sacred drinks hold their shape for centuries without picking up odors. In Japan, they carve bonsai stands and teaspoons from it. The contrast of red against white porcelain is stunning. Sushi knife handles are status accessories running hundreds of dollars. Red sandalwood is beloved by masters of the bamboo flute tradition, where the tone comes out soft yet deep. Guitars with red sandalwood fretboards sound warm, with exotic overtones. In India, they make mridangams from it, drums for temple rituals, where the wood's vibrations amplify the meditative effect. Buddhist prayer beads, Hindu jewelry, ritual cups, red sandalwood is considered a conductor of spiritual energy. In Tibet, they carve prayer wheels from it. In Japan, tea ceremony spoons. Veneers go into premium furniture for yachts and palaces. The wood doesn't fear salt water or heat. Processing demands ritual. Dried in darkness for 2 years. In light, the red fades. Cut slowly with sharp tools, the dust is toxic. Work in masks. The finish, natural sandalwood oil or carnauba wax. Heat treatment at 300 degrees makes it black-red, fire-resistant. Turning isn't just about shaping. Masters combine techniques. Roughing cut. They remove bulk, reveal the shape. Deep hollowing. For bowls, goblets, where the tool bites deep, creating walls 2 millimeters thick. Taper turning. For graceful candlestick stems. Final sanding. Grit from 40 to 2000, then oil for shine and protection. Pros add segmented turning. They join rings of different species, like a puzzle. A vase from 10 types of wood. Or texturing. Carving patterns with the tool that come alive when spinning. Heat treatment. Wood heated to 400 degrees Fahrenheit, making it fire-resistant and darker. African blackwood ebony. The darkest treasure of the tropical forests of Cameroon, Ghana, and Nigeria, where it grows slowly, accumulating resinous blackness in its heartwood over years. The wood looks like polished obsidian, deep black with gray or brown veins creating a midnight marble effect. The surface is smooth as glass with a natural metallic sheen. Ebony is so oil-saturated it needs zero varnish. The scent is subtle, earthy, with smoky notes that linger in the workshop for hours. The physics is wild. Density 75 to 80 pounds per cubic foot. This wood sinks. Brinell hardness of 8, twice as hard as oak. On the lathe, it behaves like metal. A sharp carbide tool peels off shavings in thin black ribbons. No vibration, no tear out. Centrifugal force doesn't break the fibers. They're springy like steel cable. Bowl walls a 1/16 of an inch thick don't crack. Stems hold multiple pounds. The oiliness makes ebony indestructible. It won't rot, resists termites, heat, and salt water. Turning artistry at the edge of what's possible. From Cameroonian ebony, craftsmen make spheres just over an inch in diameter with diamond-like facets. Perfect shine without polishing. Sake or whiskey cups, status minimalism, black contrasts with clear liquid. Japanese knife handles, eternal, don't slip in hand, don't dull the blade. Often combined with silver or mother of pearl, ebony emphasizes the whiteness of the inlays. Musical instruments, legendary. Flutes, saxophone mouthpieces, double bass fingerboards, sound pure as crystal, without parasitic resonances. Ebony clarinet mouthpieces cost thousands of dollars. The material doesn't absorb moisture from the air. In Japan, they make kozue from it, bamboo inserts for flutes. Rings, bracelets, pendants. Ebony's harder than bone, polishes to a mirror shine. Veneers for yachts, palaces, Patek Philippe watches. Ebony flooring, an eternal investment, never fades, never chips. Working it, that's where the master gets tested. Dried 3 years in darkness, light dulls it. Cut slow, a dull blade gums up in the resins. Dust is toxic, masks mandatory. Finish with carnauba wax or tongue oil for that wet gloss. Heat treatment at 400 degrees turns it blue-black. There's a metal out there almost nobody ever sees, but it's what turns steel into armor. How is it that just a few grams of vanadium per ton can boost a structure's strength by tens of percent and literally lighten the weight of the world? Where does this element hide if it's almost never found pure in nature? And why is it often extracted not from ore, but from dark slag that others consider waste? Today, you'll witness vanadium's journey. Hellish furnaces, blinding molten metal, fire-colored powder, and the birth of ferrovanadium that transforms steel in an instant. And at the end, I'll reveal why control over vanadium is no longer just metallurgy, it's geopolitics. Vanadium holds a special place among industrial metals, though for most people it remains nearly invisible. It's rarely seen in pure form, it's not used for jewelry, and it's barely associated with everyday life. Yet vanadium became one of the key factors in the creation of armored steels and modern high-strength structures, without which bridges, skyscrapers, automobiles, and heavy machinery would be impossible to imagine. The history of vanadium as a metal begins in the 19th century, but it gained real industrial significance much later, when metallurgists understood how even tiny amounts of this element could radically transform steel's properties. In nature, vanadium almost never occurs in its free state. Most of the time, it's found in complex minerals and ores, particularly vanadium-bearing titanomagnetites, and also in magnetite, where it replaces some of the iron atoms in the crystal lattice. The major vanadium ore deposits are concentrated in China, South Africa, Russia, and a few other countries. Mining is typically done through open pit or underground methods, depending on how deep the ore bodies lie. Magnetite ore with vanadium impurities goes through crushing and enrichment after extraction, where they separate out a concentrate with high iron and vanadium content. At this stage, the material isn't split into individual metals yet. It's a complex mixture of oxides. Vanadium's next stop, where metallurgy becomes a true industrial spectacle. Melting magnetite concentrate happens in blast furnaces or electric arc furnaces running at temperatures over 2700 degrees Fahrenheit. Inside the furnace, a mass of ore, coke, and fluxes slowly descends, passing through zones of different heat where solid chunks first sinter together, then transition into liquid. Molten iron collects at the bottom of the furnace, while lighter components, including vanadium oxides, concentrate in the upper slag layer. When the moment of release arrives, the furnace opens, and glowing streams pour out. Liquid slag glows with a blinding yellow-orange light, flows through channels, and throws up clouds of steam when it hits air or cooling surfaces. Right there in that seemingly spent mass lies the core treasure for vanadium production. After cooling, the slag transforms into solid, brittle chunks of dark material, deliberately collected and hauled away for further processing. Next up, crushing. Big pieces of slag pass through crushers and mills, getting ground into granular material or powder. The process hums with machinery, vibrations, and clouds of fine dust, immediately sucked away by filtration systems. The pulverized slag is prepped for chemical treatment, where vanadium needs to be extracted from an incredibly stable oxide matrix. Then the material enters reaction tanks filled with aqueous solutions of alkalis or salts. Under controlled temperature and constant stirring, leaching takes place. Vanadium compounds gradually transition into solution, shifting its color from pale yellow to rich orange or reddish. These visual changes directly indicate metal concentration and allow operators to monitor the process in real time. The resulting solution undergoes several purification stages. It's filtered, removing insoluble impurities, followed by precipitation, adding reagents that selectively bind vanadium. Inside the reaction vessels, a fine precipitate appears, gradually compacting and separating from the liquid. After washing and drying, this material becomes vanadium pentoxide, a bright powdery substance with a distinctive yellow-orange hue. From this moment on, vanadium stops being a hidden component in slag and becomes an independent industrial raw material. Vanadium pentoxide is then used to produce ferrovanadium, or is reduced to its metallic state. This entire sequence, from blinding molten metal to fine powder, vividly demonstrates how, deep within metallurgical processes, a material is born that defines the strength and reliability of modern steel. China produces 70,000 tons of vanadium annually, far exceeding the output of other countries and making it the global leader in both production and consumption of this metal. In terms of consumption, 90% of all vanadium goes into metallurgy, especially into high-strength microalloyed steels, where small additions of vanadium significantly increase mechanical strength, impact toughness, and fatigue resistance of structures. Ferrovanadium production is the critical link between chemical vanadium enrichment and the steel industry. It's in this alloy form that vanadium is most conveniently introduced into steel, precisely dosing its content and ensuring uniform distribution throughout the melt. The primary raw material for the process is vanadium pentoxide, obtained after processing slags or ores, along with metallic iron or iron-containing alloys. The process begins with charge preparation. Vanadium pentoxide is mixed with reducing agents, typically aluminum or silicon, and iron in strictly defined proportions. Next, the mixture is loaded into crucibles or electric furnaces, where conditions are created to reduce vanadium from its oxide state. Temperatures in the reaction zone reach over 3,600 degrees Fahrenheit, and it's at this moment that one of the most intense stages in the entire production line occurs. During aluminothermic or silicothermic reduction, the reaction proceeds extremely rapidly and releases a significant amount of heat. Vanadium oxides surrender their oxygen to the reducing agent, while pure vanadium transitions into a molten state and immediately dissolves in the iron. The result is liquid ferrovanadium with a specified metal content, typically ranging from 40 to 80% vanadium, depending on customer requirements. After the reaction completes, the melt is held to stabilize its composition, then poured into molds. As it cools, the ferrovanadium crystallizes, forming solid ingots or granules with a characteristic dark gray surface. The material is then crushed to a convenient size, packaged, and shipped to steel mills. The main value of ferrovanadium lies in its predictable behavior in molten steel. It dissolves quickly, is barely lost during melting, and allows precise control over microalloying. That's exactly why ferrovanadium became the standard form of vanadium supply for producing high-strength steels, from building structures to automotive components and armored products. The key feature of vanadium is that it works in microdoses. To get a noticeable effect, just tenths or even hundredths of a percent are enough. This means that for 1 ton of steel, only grams of vanadium are used, but those grams can boost yield strength, toughness, and durability by tens of percent. At the scale of millions of tons of steel, this delivers massive savings in metal, energy, and transportation costs. That's exactly why vanadium is often called the metal that lightens the weight of the world. Few people realize that vanadium also plays a role in long-term durability. Its compounds slow down grain growth at high temperatures and under repeated loading. This means structures made with vanadium steels age more slowly, handle cyclic loads better, and withstand sudden temperature swings. In real-world conditions, that translates to years of extra service life without repairs. Vanadium has become a critically important metal for infrastructure, and many countries have added it to their strategic materials lists. Control over vanadium flows means control over steel quality, and therefore over construction, transportation, and defense capabilities. This factor is increasingly shaping the geopolitics of metals. Every year, the world generates hundreds of millions of worn-out car tires. That makes them one of the largest and most problematic types of solid waste our modern civilization produces. When tires reach the end of their usable life, they barely decompose naturally. Why? Because they're made from complex mixtures of synthetic and natural rubber, carbon black, polymers, and steel cord. At landfills, they take up massive volumes. They accumulate for years, and they create serious environmental risks, including fire hazards, toxic chemical release, and contamination of soil and water. At the very beginning of this technological chain sits a massive stream of used automobile tires, continuously forming across the entire world. Every single day, tires come off passenger cars, trucks, buses, construction equipment, and agricultural machinery, all worn out from tread wear, micro cracks, deformations, or rubber aging. They're no longer safe for the road. But from an engineering standpoint, they're still a complex multi-component material packed with valuable raw materials. Inside every tire, you've got layers of rubber loaded with carbon black, polymer additives, textile fibers, and steel cord that gives the whole structure its strength. It's exactly this combination that makes tires difficult to dispose of, but at the same time, incredibly valuable to recycle. Collecting these tires happens at multiple levels. They accumulate at tire shops, auto fleets, service stations, logistics centers, and specialized waste collection points. From there, they're hauled by truckload to large processing plants. When entering the facility, vehicles go through weighing to record the raw material mass. Then the tires get unloaded onto open or semi-enclosed temporary storage areas. Here they can pile up in massive stacks. Think black hills of rubber, designed for continuous feed into the processing line. Before the tires actually hit the processing stage, they undergo initial inspection and prep. Workers or automated systems check their condition, paying close attention to contamination levels. Some tires might be covered with a layer of dirt, grease, asphalt residue, or debris accumulated during use or storage. These contaminants are undesirable because they can damage equipment or degrade the quality of the final rubber crumb. That's why excessively dirty tires get rejected or sent for preliminary cleaning. Special attention goes to foreign objects that sometimes remain inside the tires. Cavities can contain rocks, metal chunks, wood, or even fasteners that accidentally got in there during operation. Before feeding into the shredding units, these objects are removed manually or with specialized mechanisms. This is a critical stage because foreign solid inclusions can cause emergency line shutdowns or accelerated wear of blades and cutting elements. This preparatory stage produces a relatively uniform stream of raw material, ready for mechanical processing. Tires that pass inspection move to the initial shredders already free of excess contaminants, allowing the plant to operate stably and continuously. It's at this exact moment that used tires definitively stop being a problematic waste product and transform into a controlled technological resource, from which materials for modern road infrastructure are subsequently manufactured. After this, the tires enter the primary shredding zone. Here, massive industrial shredders with slow rotating shafts and cutting teeth do the work. Each tire is grabbed by the mechanism and literally torn into large fragments several inches in size. The process involves significant mechanical stress and noise, so equipment is housed in enclosed units with dust collection systems. Even at this stage, some of the steel cord begins separating from the rubber, but the main separation happens later. Shredded fragments are conveyed by belt systems to the next crushing units. Here the material goes through several size reduction stages, gradually transforming into rubber crumb. Magnetic separators work simultaneously, extracting steel cord and wire. Magnets are positioned above conveyors or built into drums, and they continuously separate metal, which drops into separate containers for further processing as scrap. Textile fibers used in some tire types are separated using airstreams and vibrating screens. At the output of this section of the line, cleaned rubber crumb of various fractions is formed. It's additionally screened to achieve a stable particle size distribution. For rubber-modified asphalt production, controlled particle size is critical because it determines exactly how the rubber will interact with the bitumen. Oversized particles distribute poorly in the mix, while particles that are too fine can behave almost like filler and alter the bitumen's viscosity more than needed. Before blending with bitumen, the crumb is typically dried and heated. Even a small amount of moisture can negatively impact the quality of the final mix, so the material is passed through drying drums or chambers with controlled temperature. Heating also makes the rubber more elastic and prepared for contact with hot bitumen. At this stage, the plant is already handling material flows measured in tens of tons per hour. Meanwhile, in another part of the facility, they're preparing the bitumen. It's stored in large insulated tanks and kept heated so it stays liquid. When it's time to mix, the bitumen gets pumped into special reactor mixers or kettles, where they gradually add the rubber crumb. The temperature in these units is typically much higher than in regular asphalt production, because the rubber needs time and heat to start interacting with the bitumen. During mixing, the rubber crumb particles absorb the lighter fractions of bitumen and swell. This isn't just mechanical stirring, it's a physico-chemical interaction that transforms the binder's properties. The mixture becomes more viscous and elastic, handling temperature swings and traffic loads way better. Mixers run for a set amount of time to hit that uniformity sweet spot, and then the rubber bitumen blend is ready to roll or store temporarily. From there, this material either heads straight to asphalt concrete plants or gets hauled in special insulated tankers. At the plant, it becomes the binding base for producing asphalt concrete mix with crushed stone and mineral fillers. The finished rubber-modified asphalt is laid down pretty much the same way as regular asphalt, but it behaves differently once the road is actually in use. Roads with this surface dampen vibrations better, produce less noise from tire contact with the pavement, and maintain their integrity longer without cracking. The elasticity that rubber provides allows the surface to better handle temperature swings, especially important for regions with cold winters or scorching summers. This reduces the need for frequent repairs and extends the overall life cycle of the road. At the plant scale, this entire process looks like a continuous flow of materials, where waste gradually transforms into an engineered product. Millions of old tires that would otherwise sit in landfills or illegal dumps for years become part of road surfaces. This not only reduces environmental impact, but also allows for partial replacement of virgin materials, cutting down on resource consumption. That's why rubberized asphalt is increasingly viewed not as some exotic option, but as one of the practical directions for modern road construction. In the United States, the problem of disposing of worn-out car tires is massive too. Estimates show that roughly 300 million old tires are generated annually in the US, a huge waste stream that demands effective management and recycling. The good news? The situation has improved dramatically over the past few decades. Back in the 1990s, the US had over 1 billion old tires sitting in stockpiles. But thanks to government programs and a growing recycling market, that number has dropped by more than 90% to a significantly lower level in the 2020s. Imagine a metal that looks like a liquid, moves on its own, and for centuries was thought to be the key to immortality. What if this very substance drove scientists insane, killed entire cities, and still hides underground today, waiting for human error? Every year, the world produces and isolates thousands of tons of this stuff. But the real danger isn't in the numbers. It's that mercury never disappears. It migrates, it accumulates, it comes back. From alchemists who breathed in its vapors to tragedies born from normal water and fish, this is the story of a metal humanity called poison way too late. Stick around till the end, and you'll learn why even today, mercury isn't seen as a resource. It's a threat you can't just bury. In ancient civilizations, people knew about mercury long before they understood how dangerous it was. They found it in nature as cinnabar, a bright red mineral that released mercury when heated. Chinese alchemists thought it was an ingredient for immortality. Egyptians used it in rituals. Romans put it in mirrors and cosmetics. Spoiler, none of this ended well. But back then, nobody was reading safety labels. In medieval times, mercury became the star of alchemy. It symbolized change and transformation because it could be both metal and liquid at the same time. Alchemists believed it was the key to making gold. They breathed its vapors, touched it with bare hands, mixed it with other substances, and genuinely wondered why their hands were shaking, their memory was failing, and weird psychological symptoms were kicking in. That's how the mad scientist trope was born. No memes required, just real consequences. The modern era brought mercury an even bigger upgrade. It was used in thermometers, barometers, manometers, fluorescent lamps, batteries, switches, and even medicine. Yep, Doctors once prescribed mercury as medication, for infections, even for bad moods. The biggest fail? Treating syphilis with mercury ointments. The disease might not go away, but poisoning was guaranteed. Who remembers mercury thermometers? Drop a comment if you've got one. It was in the 20th century that humanity started to collectively realize mercury wasn't just weird, it was genuinely dangerous. It's toxic in any form, but especially sneaky because it evaporates easily and builds up in your body. Nervous system damage, coordination problems, memory loss, vision issues. This isn't some thriller script, it's what chronic mercury exposure actually does. The phrase "mad as a hatter" didn't come out of nowhere. Hat makers used mercury compounds, and craftsmen literally lost their minds. Then there's the dark chapter of ecology. Mercury doesn't disappear, it migrates. When it hits water, it transforms into methylmercury and enters the food chain. Fish eaten by humans, and suddenly the toxins inside you. The tragedy of the Japanese city of Minamata became the symbol of this problem. Mass poisoning affecting thousands of people proved that a little mercury is a myth. In the mid-20th century, in the Japanese coastal city of Minamata, a chemical plant spent years dumping wastewater loaded with mercury compounds into the bay. The water looked normal. Fish were biting. Life went on, until people started getting mysteriously sick. First came the seizures, tremors, loss of coordination, speech problems. Then, paralysis, blindness, death. Mercury hit children especially hard. Infants were born with severe nervous system damage, even though their mothers often showed no obvious symptoms. The culprit was methylmercury, accumulating in fish and shellfish, the foundation of the local diet. The toxin didn't disappear or dilute. It intensified at every level of the food chain. For decades, the company and authorities denied responsibility, while victims fought not just disease, but indifference. Minamata showed the world a simple, brutal truth. Even minimal doses of mercury can have catastrophic consequences when they become part of the environment. It was the end of the illusion of safe mercury. Mercury deposits exist today, but attitudes toward them are radically different from centuries past. The primary natural source of mercury remains cinnabar, a bright red mineral, mercury sulfide, which forms in hydrothermal deposits, often near volcanic zones, and fractures in the Earth's crust. It's from cinnabar that metallic mercury was historically obtained through roasting, and this process has remained virtually unchanged technologically. What changed were the scale and the regulations. The largest known mercury deposits in the 20th century were developed in Spain, Italy, China, Kyrgyzstan, Mexico, and Algeria. Spain's Almaden deposit was once considered the world's largest, and for centuries supplied a significant portion of global production. Today, it's basically mothballed, like most classic mercury mines. The reason's simple: demand tanked, and the environmental and health risks became too obvious to ignore. China remains the main mercury producer now, but even there, extraction volumes are way lower than in the past. Many countries aren't opening new deposits. They're working with existing stockpiles or secondary mercury recovered from industrial waste recycling and dismantling old equipment. The world has essentially shifted from active mining to a mode of control and reduction. Modern mercury deposits are increasingly viewed not as a future resource, but as a problem that needs to be safely isolated. Some deposits get shut down, others are reclassified as geological landmarks or monitoring sites. Mercury still sits deep within the planet's core, but its story as a strategic metal is nearly over. Now it's an element humanity handles with extreme caution. Underground mercury ore extraction in China typically starts with a narrow portal carved into rock, the entrance to a mine shaft. It might look like a dark rectangle in stone, reinforced with concrete or metal frames. Inside, a tunnel several yards wide, where small mining vehicles can pass through or conveyor belts can run. The working space is cramped and low. The ceiling's propped up with beams, the walls damp, streaked with reddish or dark brown veins of cinnabar. Lighting. Cold fluorescent lamps casting harsh shadows. The air's heavy, so ventilation is critical. Along the tunnels run air ducts, humming and pushing fresh air deep into the mine, while simultaneously pulling out dust and gases. The ore itself is extracted using drill and blast or mechanical methods. First, drilling rigs bore a series of holes into the rock. It looks like rhythmic metal biting into stone. Then, if blasting is used, minimal charges are placed in these holes. The explosions are controlled, small. The goal isn't to destroy everything, but to peel away the rock. After that, the tunnel fills with dust that settles for minutes, while ventilation runs at full blast. Next, mechanization takes over. Front-end loaders rake up the broken rock, or gather it in buckets and dump it into mine cars or onto a belt conveyor. The stone looks uneven, with flecks of red. That's cinnabar, the main target. People try not to touch the ore with bare hands unless they have to. The dust is dangerous, so workers wear respirators, thick coveralls, gloves. How strictly this is enforced depends heavily on the specific operation. If it's a semi-underground or open-pit mine, the picture is different. There you'll see step-like benches cut into the rock where equipment moves around. Excavators strip away layers of ore, trucks haul it up to the surface. But even here they try to avoid huge open spaces, mercury dust and fumes, enemy number one, which is why open pits are less desirable for this kind of metal. All that ore doesn't sit around in the mine for long. It's immediately transported to the surface in sealed containers or on covered conveyors to minimize dust dispersal. At the mine exit, you'll often see washing stations, equipment, and sometimes the workers themselves get hosed down so they don't carry cinnabar particles beyond the production zone. After extraction, the ore is crushed and sent for heat treatment. Cinnabar is heated in specialized furnaces, where the mercury sulfide breaks down and the metal evaporates. This stage is the most dangerous. Mercury vapors are toxic, so modern facilities are equipped with sealing, condensation, and filtration systems. The vapors are cooled, after which the mercury transitions to a liquid state and is collected in sealed containers. Formally, all these processes are supposed to occur in a closed loop with no emissions into the environment. In practice, this is where the biggest questions arise. At large state-run or licensed operations, oversight is stricter. There's air monitoring, waste disposal protocols, and tracking of every kilogram of metal. At smaller or semi-legal operations, the risks are significantly higher, and these have historically been the source of local contamination and poisoning.